Hello everybody and welcome to Introduction to Measure Theory. This will be a series of slides that briefly summarize the important concepts in the first three chapters of Gary B. Fullen's Introduction to Real Analysis. Attached below is a summary PDF file which will provide some detailed proofs that might not be covered thoroughly in the video. We will illustrate the importance of measure theory by asking a question whether we are able to pass the limit inside the integration for all sequences f and x. Although this property is intuitive and makes sense, we can see that this property does not always hold in Riemann calculus, as we can consider the following sequence and note that although the limit of this sequence exists and converges to a specific function, the Riemann integration of this property of this function does not exist. Thus, we can see that Riemann calculus has some shortcomings, and these shortcomings are addressed by measure theory, since measure theory provides a more general framework that can cover these problems, such as types of functions not being closed under limits, or Riemann integration not existing for unbounded functions. The definitions in measure theory also extends the scope of integration beyond classical calculus, and it provides greater tolerance towards functions that behave strangely on specific points.
Before we can discuss measures, we need to introduce the idea of a measurable space. A measurable space consists of two components, the big set X and a sigma algebra. X and sigma algebra are both general and are often chosen based on the context of the problem. So for example, if we're interested in analyzing age dynamics, X would be the set of all non-negative real numbers. A dice throw, X would be 1, 2, 3, 4, 5, 6. Sigma algebras, however, are often constructed around a family of sets that we're interested in. Oftentimes, we're extending this family of sets so that it fulfills the properties of the sigma algebras so that we can perform operations on it that are closed. We can generate a sigma algebra around a set by taking the intersection of all sigma algebras that contain this family of interest. We refer to that sigma algebra as a sigma algebra generated around that set. Note that this property of the sigma algebra results it being closed under all set operations, which is one of the reasons why we want to extend our family to a sigma algebra. Two examples of a sigma algebra could be the power set and the empty set. It's easy to see that both are closed under countable unions and complements. And note that because the power set contains every possible family of set, we can always construct a sigma algebra. When X is a measurable space, an important sigma algebra is the Borel sigma algebra, which is a sigma algebra generated around the family of open balls. The importance of the Borel sigma algebra will be shown later on when we're operating on R or Rn. If we further limit the metric space to be R, the Borel sigma algebra can also be generated not only by open intervals, which is the ball on R1, but it can also be generated by closed and half intervals. Each results in the same, each method, results in the same sigma algebra, so this sigma algebra is well defined. Now that we specified the domain of the measure, we can define the measure itself. A measure is any mapping from the sigma algebra to the non-negative real number system. It fulfills two properties, which are listed on the screen right now, and these are the ideal properties that serve as the axioms we want measures to follow. Sometimes we extend the real number system to include the element infinity, which is a symbol that's greater than all other numbers. It possesses the intuitive algebraic and properties. So infinity plus anything is still infinity, etc. But the most important thing to note is that we define 0 times infinity to equal 0. By ensuring additivity and the measure of the empty set is equal to 0, we can prove that measures also fulfill several desirable properties, such as continuity from above and below. So once we have a measurable space, we can define a null set on a sigma algebra. A set E is said to be null if the measure of the set is equal to 0. Null sets are interesting because we are often uninterested in how certain properties behave on null sets as their measure is 0. Properties that hold for every point that's not in a null set is said to hold almost everywhere. And in later slides, we will introduce something known as the big measure. Since the big measure of any individual point is 0, using this measurable space, we can ignore inconsistencies if the measure is 0. For example, we can say that the function y equal to absolute value of x is differentiable almost everywhere with respect to the big measure, which is in most real-life applications just as useful as being differentiable everywhere. That's fine.
This video will use a binomial tree to show how sigma algebras can handle information filtration. Our goal is to price a financial contract, also known as an option, that is dependent on an underlying stock. In this case, we will assume that the stock follows a two-step binomial model. Let FTS denote the value of the option at time t, where S represents the information of the stock. In this example, X would be the fourth possible path, and we can define three separate sigma algebras, M0, M1, and M2. Each measurable space corresponds to their own set of measurable functions. We say that the pricing process FTS is legitimate if it is only based on the information up to time t. If two paths, omega 1 and omega 2, are the same from time 0 to 1, then ft omega 1 must equal ft omega 2. In this example, f0uu must equal f0ud, and f1uu must equal f1ud, but f2uu does not have to equal f2ud. This is because uu and ud only start to differ at time 2. So at time 0 and 1, in order for this FTS pricing process to be legitimate, they must equal. We can prove that measurable functions with respect to the MT sigma algebras are the same as the legitimate pricing process as time t. The details of which are shown on the screen right now. And this example shows how we can quantify this property using sigma algebras, since for any information process, we can find a measurable space such that the process is legitimate if and only if it's a measurable function with respect to said measurable space. In the previous example, we found that it was rather simple to construct the sigma algebra around the family of sets. However, in continuous or complicated discrete cases, it is often difficult to find the intersection of all possible sigma algebras. This section will focus on how to construct a measure space using something known as an outer measure. Although we are constructing a sigma algebra and a measure, oftentimes we are starting off with the initial family of set and an initial map that is often predetermined based on the context of the problem. We want to extend this map and this family of sets to a measure space because we will be able to use the properties and the operations on the measurable space. This could include things such as the measurable functions associated with the sigma algebra. So given family delta and map rho that fulfills the following two trivial conditions, we can define mu star in the following manner, and this mu star will be something known as an outer measure. An outer measure is a map that maps from the power set to the extended non-negative real numbers space, and it satisfies the three following conditions right here. The importance of an outer measure mu star is that we can then define set A to be mu star measurable if it satisfies the following condition. The importance of mu star measurable sets is shown through Carat-Theodory's theorem, which states that the collection of all mu star measurable sets of an outer measure is a sigma algebra, and by restricting the outer measure mu star onto the sigma algebra will generate a complete measure. Although this method generates a measure space that contains the initial family of interest, the problem is that it might not preserve the initial map that we defined on rho. For example, if we set rho from 0 to 1, the interval 0 to 1, to map to 1, the final measure might map it to something else, such as 5. And this is a problem because oftentimes we want our measure, the resultant measure, to satisfy some conditions that we place on it, which are the maps that we have on rho. To circumvent this issue, we can put some more conditions on our initial set of interest and the map rho. And when the initial set of interest is an algebra and the map rho is a premeasure, we can see that the final constructed measure fulfills the properties that the restriction of the measure to the algebra is the same as the original premeasure, and if the original premeasure is finite, then the resultant measure is the unique extension of the original premeasure. Although it might seem kind of redundant to reduce the issue of constructing a measurable space to having to have a algebra and a premeasure to start off with, we can see that constructing an algebra and constructing a premeasure is much more simpler than constructing a sigma algebra and constructing a measure, because we no longer need to fulfill the infinite. We no longer need to deal with infinites. As we can recall, an algebra is any set that is closed under finite unions and complements compared to sigma algebras, countable unions and complements. And we will see how much easier it is to generate an algebra in the next section.